Hello friends, welcome again to the tetrahedron chemistry classes. So in the spectroscopy MCQs lecture series, today I am going to discuss the spectroscopic problems which have been asked in the June 2019 examination, and we'll cover only 5 problems today, as some of the problems in this June 2000 examination actually is a little typical type, so maybe like that we will consume a little more time. So I have restricted my lecture up to June 2019 problems only. In the next lecture I will discuss the December 2019 problems, okay, and later on we will discuss the Northeast paper also. So in today's lecture, my first problem in the June 2019 examination is like that. You can see what is the problem here. The number of the proton NMR signals observed for the following compound, right? You have been given this compound, it's a bicyclic compound, okay, and you have to select out of these 4 A, B, C, D, 3, 4, 5, 6 which one is the correct answer, okay. So these kinds of the problems or the stereochemistry of such compounds I have already explained in my earlier lectures, okay. So but today I am again going to discuss all these things. So first of all, what I will do, I will put all the protons which are there. So this is your methyl group, so I can write CH3 for this one, and similarly this is also your CH3. One hydrogen is there, okay, and another hydrogen is here, and then you see another hydrogen is here, and my next hydrogen is here, okay, and these are the 2 hydrogens which are at the bridge carbon atom, okay, here like. So if you focus on this structure, right, then you will very easily find this molecule is having C2 axis of symmetry, which actually passes through the center of the molecule. How? You see, if this is the molecular axis, so through this molecular axis a C2 axis will pass. But to understand all these things, you should have the little idea about the symmetry elements, how we actually predict the types of the symmetry elements present in the simple molecules, okay. But I am telling you, this is the molecular axis, and along this molecular axis I am having my C2 axis. So how I can draw my C2 axis here, say just like that, through the center of the molecule, right? Here, this is my C2 axis, and you know what is the meaning of the C2 axis. If I say C2 axis is there, that means if I rotate the molecule through this molecular axis by 180 degree, then I will have the another picture of the molecule which would be exactly identical to the previous one, okay. So based on this, if you see, if I rotate, right, if I rotate this molecule just like that, you see this methyl and this methyl, they are at 180 degree angle, right. So this methyl will be exchanged with this methyl group, so they are actually symmetry equivalent. So this methyl and this methyl, since they are at 180 degree angle and we are rotating the molecule through C2 axis, these two are the equivalent one, okay. So what I will do, I will write this methyl group as the proton type 1. So I can write as proton type 1. This is also the proton type 1, okay. Next you see this hydrogen, right, as well as this hydrogen, they are also at 180 degree angle, okay. Not exactly, see in the picture you will not look, it will not look like that these 2 hydrogens or these 2 methyls are at 180 degree, but I am telling you, if you draw the model of this one, these are at 180 degree angle. So this after the rotation of the 180 degree, this hydrogen will exchange with this one, so that means these 2 hydrogens are of the same kind. So I can mark this hydrogen also, right. This is say type 2 hydrogen and type 2 hydrogen. So this is enough to explain you how we can decide the identical nature of the hydrogen. So based on the similar argument, this hydrogen, these two are also equivalent, so I can mark them as hydrogen type 3 and hydrogen type 3, right. And then after that you see these are, see if you focus on these one, so this hydrogen is going actually below the plane and this hydrogen is actually coming out of the plane, so they are also actually equivalent in nature. So when I rotate this one, so after the 180 degree rotation, this hydrogen will come here and this hydrogen will go there, just like that. This 2 will come here and this will come here, right. So these 2 hydrogens are also equivalent due to this C2 operation. So I can mark them also, mark these hydrogens also. So this is type 4 and type 4, right? So only you can see the 4 types of the hydrogens are there, 1, 2, 3, 4. So in the NMR spectrum, proton NMR spectrum, I will expect only 4 kind of the protons. So in that case, my correct option would be option number, where it is given, yes, option B is the correct option. 4 signals total I will get in the proton NMR spectrum. But to understand such kind of the problems, you need to understand the symmetry elements present in the molecule. Now moving to the next problem, what it says that, okay, this is your next problem. The compound that will show a base peak at 120 in its electron impact mass spectrum, and you have to decide out of these 4 compounds which one actually will give you the peak somewhere around at m by z 120, and it would be a base peak, right? The question says that it would be a base peak. So how to actually approach such kind of the problem? I have explained all these kinds of the problems in pretty much detail in my mass spectrometry lecture, and as well as in the previous year CSIR net examination, I have actually explained the concepts so many times, but again I am going to explain how to approach such kind of the problems. So for this, first of all, you need to understand all these molecules, right? Say if you draw any one of them, and if you calculate the molecular weight of these, so all are having the molecular weight of 152, and all these are the positional isomers or say functional isomers of each other. So all these have 152 molecular weight. It is, see, you can calculate by your own. The molecular ion would be around at 152. So you cannot actually differentiate based on this molecular ion. So how to approach such kind of the problem? Say if, what the question is asking, actually question is asking, we should have a that means we are having a peak at m by z 120. Okay, so how we can do that? Say first of all, your molecular ion, this is your molecular ion which is having 152 m by z value. Okay, there is no problem in that, and you need a peak at 120 m by z. So if you take the difference of these two, right, if you take the difference of these two, so what I can do, I can put negative sign here. Okay, so when you subtract these two, then you will find you will have the 32, right? So that means one of these molecules, right, must remove this 32 unit from it, right, to give a peak at 120. This is a little trick you need to understand. Okay, and if you know what actually this 32 actually will correspond to which kind of the molecular formula, so you should know, you should have the little idea about the neutral losses in the molecule. Say your molecule can lose this C2H4 methylene, right, ethylene, sorry, right, and sometimes it may also lose your CH2OH, right, and it may also lose CH3OH, right. So this is the neutral losses which generally occurs, right. And if you check the molecular weight of this methanol, right, see, carbon is 12, hydrogen is 3, hydrogen is 16, and again hydrogen is 1, this will give you 32, right. That means you should remove CH3OH molecule out of any one of these, right, from any one of these you should remove CH3OH in order to get the peak at 120, sorry, not 1 by 20. So we can approach the problem systematically. You see here, this molecule is having OMe here, and one hydrogen is here, one hydrogen is here. If you remove hydrogen from here, right, so and so it will actually disturb the aromaticity, and no other hydrogen can come here actually, right. So this actually, and moreover, you see they are actually very farther apart. So there are no, see, there is no hydrogen, right, apart from these aromatic hydrogens, there are no hydrogens which can actually remove from this system. So this A actually cannot be your answer. So what you can do, you can discard this option A. Straightforward, you can discard option A. Similarly, you can go for the option B. You see this COH is here, right, here COH is here, MEOH is here. So their distance again very high, right. This is your meta isomer, this is your para isomer. Their distance is quite large in that case. So there should be no, there would be no interaction between this MEO and hydrogen here. and MEO and hydrogen here. So this B can also be cannot also be your answer. So you can discard option B also, right? And then you can look for the option C. Option C is this OH and this CO2 Me. Let's check whether it is possible or not. So for this, what we can do, we can draw the scheme. First of all, say you are having this species, okay, you can draw like that, and this is your C double bond O, and then your O, and then your CH3, right? This you are having, and somewhere here you are having OH group. So basically I am drawing for this one, right? Please remember I am drawing for this one. So once you form the molecular ion, how the molecular ion will form? One electron will be knocked out from here, and this would be your molecular ion. Now you can see it is quite obvious that this CH3OH is here with very acidic hydrogen. You know this H hydrogen, this hydrogen is very acidic. So this CH3O can take this hydrogen, and removal of CH3OH can occur from here. While in this case you can see these hydrogens are not that acidic, right? Similarly, these hydrogens are not that acidic, right? So we cannot remove hydrogen from here. We need the acidic hydrogen in that case, and we know the alcohols are acidic in nature. So how we can do this problem? You see, this hydrogen. See, first of all, this bond will break from here to here. So this electron pair will come here, okay, and this electron will go there, and this will come here, and this will go there, and this hydrogen along with the electron pair will attack on this oxygen, okay. And when you do that, what will happen? The removal of the methanol would occur, CH3OH, okay. Basically it's alpha cleavage, guys. It is alpha cleavage, right? Why alpha cleavage? You see here, this is the functional group, this is your alpha position, okay, and this is your beta position. So you are breaking the bond, carbonyl bond after you are breaking the bond after the carbonyl group, okay. So what you left with then? You left with this benzene ring, okay, and your electrons, these two electrons actually has moved right way, in that way, and in that case you see this has come here, this would be carbon double bond carbon now, okay. So what I can do, I can write double bond carbon, and you know this double bond oxygen is already there, so I can put that double bond oxygen here also, okay, of course with positive and dot like that, and to this, and then this would be your double bond oxygen, right? How double bond oxygen? Because this has moved from here to here, this has come here, this is double bond. So this species we get actually. And if you calculate the molecular weight of this one, the molecular weight of this is M by Z value is 120, right? So it is giving this value, and this is quite a stable species, right? This is quite a stable species because it can regain the aromaticity. It will have the resonance structure. See, if you want, then you can draw the resonance structure also. How actually the resonance structure would be drawn in that case? See, one electron will from here will come here, and one will go there, and one electron will go there, and another electron will come here, and another electron will go there, and then you will have this species. This single bond carbon, triple bond oxygen with positive, and your oxygen with dot. Okay, so this is a resonance stabilized structure. So this is giving at 120 value. This is giving the 120 value. That means my option C is looking the correct option. So I can mark my option C as the correct option. If you want, then you can go for this one also, right? This one also, but this is, you see, again it is not possible because this is methoxy, right? OMe, and this hydrogen is there, right? This hydrogen is there, but their removal is quite difficult. If you want to draw the mechanism, you can do by your own. And if you have any confusion, about that, then you can comment in the comment section. I will try to answer with the best of my capabilities. Now moving to the next problem, what it says that, okay, this problem, what it says that The compound that exhibit the following spectral data, your IR stretching frequency at 1685 centimeter inverse, and proton NMR 7.84 doublet, 7.60 doublet. So again, see guys, I am having two doublets here, and in the aromatic compounds, when we are having the two doublets, it simply means that my para-di substitution is there, right? Two doublets means para-di substitution, para-di substitution. That means whatever the answer will have, okay, that should have the para-di substitution. And you know this option D is having your, see, this is your principal, this is the principal functional group, this is ortho position, and this is your meta position. So this D cannot be your answer. So what you can do, you can very easily discard this option D. Okay, this cannot be your answer. So I can remove this one. Now moving to the next problem, right? See, other options actually are quite tricky and quite close, but you have to look for the spectral data very carefully. So here a very important hint is that in the question your IR value is given 1685. So let me correct it. It is given 1685, right? And see, near about 1700 you are having your ketone value. So this is more close to the ketone value. Basically this 1685 correspond to the alpha beta unsaturated ketone, right? Or sorry, conjugated ketone, right? Alpha beta conjugated ketones. So this is conjugated ketone. Conjugated ketone. And to decide the conjugated ketone, you should know a very important fact here. This is your, see, option C. If you look the option C is the acid chloride, right? So when you have this acid chloride here, right? So due to the acid chloride, you can apply the various concepts here of your general organic chemistry. But I am telling you straightforward what can happen. Due to the presence of this chlorine, this carbonyl actually resonate at the higher frequency, or you can say the stretching frequency is quite high, and it's somewhere around 1800 centimeter inverse. So for carbonyl, please remember, for the carbonyl group which is in the form of the acid chloride, for this near about 1800 centimeter inverse is there, which is quite a high value. So based on this, what we can do, we can discard this option also, right? This cannot be your answer. Option C cannot be your answer, because this acid chloride should have the stretching frequency, this carbonyl stretching frequency should have the around the 1800 centimeter inverse. Okay, now you left with the option B and option C, right? If you check this option B and option C, okay, both these compounds will give you the exactly similar kind of the proton NMR spectrum. And when the proton NMR spectra for these two compounds are generally the same type, then it is very difficult for us to differentiate between them. If someone says that we can actually differentiate between these two compounds based on the proton NMR spectroscopy, so I'm sorry, it is not possible, right? It is quite confusing. So first of all, you can see here, if I am going for the option B, right? Say for example, if I am going for the option B, so this option B is having the two protons here, okay? And when it is having the two protons here, so it will have the chemical shift around 3.6 ppm. 3.6 ppm, and that 3.6 ppm is there in the proton NMR spectrum. Where is, yes, 3.6, exactly 3.65 is there, which is a triplet, right? Of course it is a triplet because in the neighbor two hydrogens are also there, right? At this position, right? At this position two hydrogens are there. And if you check these two hydrogens, so two hydrogens are here and two hydrogens are here, so it will produce a quintet. And that quintet, what the proton NMR says, it is around 2.25. So what you can do, you can write its chemical shift also 2.25. Okay, and then you left with this CH2. It is again in the environment of these two hydrogens, so it will give you a triplet, right? But that triplet due to this carbonyl group would be around somewhere 2.2 ppm. So you can write the chemical shift of this also 2.2 ppm, right? Or 2.0 ppm to be exact. I think what is given in the question we can check here. Here you can see, yes, 3.65 a triplet, 7 these rest are okay. There is no problem in that, we can write in that manner. Okay, and then the chlorine is there, then you can think in that manner. These two hydrogens, they are the equivalent, and these two hydrogens are also equivalent because this is paradise substitution. The plane of symmetry is there, so these two are equivalent. Okay, and if you want to know the chemical shift, the chemical shifts are very close for them, like that. For this 7.8 ppm, for this also 7.8 ppm, which is given in the question again. For this is 7.3, this is again 7.3. So this is little upfield, right? Why little upfield? Because electron donating effect of chlorine is there. While in that case, why these two hydrogens are having the little high or downfield chemical shift? Due to the presence of this electron withdrawing carbonyl nature. But if we check the proton NMR spectrum of this compound also, so roughly you will get the same kind of the chemical shift. So it is very difficult for us to differentiate between them. So from where actually we will get our answer? We will get our answer from this. You see, from the spectrum. Here what is written here? You see, you will get the two peaks at m by z value 200 and m by z 198. So this is actually your molecular ion, and this is your m plus 2 peak. Similarly, you see 185 and 183. So 183 is your ion, and this is your m plus 2 ion. You know, m plus 2 ion is possible in case of the brominated compound. But again the problem is there. This molecule is having the bromine here, and this molecule is having the bromine here. So how we can decide? We can straightforward go for the their mass spectral fragmentation pattern. So first of all, I am doing for this first option B, right? I am doing for the option B. I can write the option B here, and I can put my chlorine here, and these electron rings are there, and this is where, just like that, I can write this. Okay, and then you can see here, this is your alpha carbon, this is your beta carbon, this is your gamma carbon, and these two gamma carbon is having two gamma hydrogens. So you can apply the McLafferty rearrangement here. McLafferty. This is McLafferty rearrangement. Okay. McLafferty rearrangement. So McLafferty rearrangement is what? Transfer of the gamma hydrogen to the unsaturated system. So basically one of the hydrogen will transfer from here to here. Okay. So when the McLafferty rearrangement will occur, what will happen? The alpha cleavage would be there, and due to this alpha cleavage, you see this bond will break. Alpha beta bond, this bond will break. So how actually it happens, I have explained to you so many times, but again I am giving you the idea how we can do this. What I can do, I can remove one head of the arrow. It is showing now the movement of only one electron, and already I have formed the molecular ion for this one. So one electron will transfer from here to here, and another electron will come here. Alpha beta cleavage would be there, so this electron will come here and this will come here, and in order to compensate the electron deficiency, it will come here and one electron will come here. So what is happening here? This Br along with this CH2, this carbon, because this bond has break, so it will remove from here, and the removed neutral species would be like that. This is Br, and then what you left with? You left with this one, chlorine here, and that species would be OH, and this is your double bond. How double bond? You see single bond was already there, right? One electron has moved from by the cleavage of this bond from here to here, and one electron is coming from this pi bond actually, right? So this is double bond, this is going up actually, and hydrogen has came from here, so this is single bond oxygen, right? So if you calculate the molecular weight of this species, right, if this molecular weight of this species, so it will come around m by z 154. Okay, because 7 carbons are there, 1 chlorine, right? It's not 7 carbon actually, 8 carbons are there, 1 chlorine, 1 oxygen, rest of the hydrogen, so it is 154. Now we can check here, we are not having any peak at the 154. That means option B cannot be your answer. When option B cannot be your answer, what I can do, I can remove it. You can take the screenshot of this one if you want. Now I can go for the option C. So what the option C says, in the option C you see, this is my system, this is my Cl, okay, and this is my carbonyl, this is say my molecular ion, and just like that you see my sorry, I actually made the earlier one. I can put my Br here and I can put my Cl here. Now again you see in that case also, this is my alpha carbon, this is my beta carbon, this is my gamma carbon, which is having the 2 hydrogens, okay. Same thing would occur, this will move from here to here, 1 electron will come here and this bond will break, 1 electron will go there, okay, and 1 electron will come here, this will go up and this will come down, and you will apply the Mc-Lafferty rearrangement. So I am writing Mr to save the time, and you remove this species from here, and what you left with, then you left with this species, okay, this OH double bond positive, okay, like just like that, okay, and at this position you are having the bromine. So if you take the molecular weight of this one, M by Z value, so this, its M by Z value is 198, its M by Z value is 198, okay. And when, if you see here in that case, you can see the 190, you are getting the peak at 198, but again you are getting the peak at 200 also. So for example, if I am taking this bromine as the first isotope, that is bromine 79, okay, then it will give you 198. But if I take this, if I replace this 79 with the 80, say Br 80, so you will 81, you will add 2 to this unit and you will get the 200, peak at 200. So this option C actually, this option A is actually satisfying all the condition. That means my option A is looking the correct answer. So in this way you can answer such questions also. So my option A is looking the correct answer. Okay, my option A is correct answer. Now moving to the next problem, what it says that. So guys, my next problem, again guys, it's a very important problem, very tricky problem, and that's why the CSIR net in the 2019 examination has asked this question for the 4 marks. The value for this of this question was 4 marks, and this question is not that easy question. Actually I took a little while to actually solve this particular problem, right? Initially when I actually solved this problem, I took a little while to understand the things actually, right? And so how we can solve such kind of the question? First of all, you should look, you should actually check the question. Reaction of the styrene. So this is a styrene, benzene, CH double bond CH2. You know the styrene monomer. When you polymerize this styrene, you will get the polystyrene, and that polystyrene is used in the water rippling clothes, wing jitters, for the formation of the for the manufacturing of the water rippling clothes, right? And see, when you react with this HBr, then you will get the 2 regioisomers. That means when we are getting the regioisomers means that means your structural isomers. Okay, it may be your functional, it may be your positional, anything. So whenever we are having these 2 isomers, that means of course your concept of the regioselectivity is applied here. But you don't need to know these things in that much of detail to solve this particular problem. But if you want, then you can go for the tetrahedron chemistry classes, right? Regioselectivity, stereoselectivity, right? And enantioselectivity, distereoselectivity. I have explained all these things in my lecture. So what you can do, you can type in the YouTube search bar stereochemistry by tetrahedron chemistry classes or stereoselective reactions by the tetrahedron chemistry classes. You will get the result in the YouTube, and then you can go through these things. And then you see when you react, when you react this styrene with this one, you get these 2 isomers, and the proton NMR spectrum actually is just like that. These chemical shifts are given here in the decreasing order. You can see this is 5.17, this is 3.53, this is 3.15, this is 2.00, and with relative integration of 2116, that means this 5.17 ppm value is having the this peak is having the integration of 2, and this 3.53 is having the integration of 1, and this 3.15 is having the integration of 1 again, and this 2.00 is having the integration of 6. Okay, so you have the NMR of the mixture. So what would be the molar ratio of A and B? We have to actually select this one, but it is very interesting problem. I like this problem. Okay, so what you can do, you can write the styrene. You can write the styrene here. So very quickly I can say this is C, this is H, this is double bond, this is CH2, and you are reacting with this HBr according to the Markov rules. So I am not going to explain the Markov rule here, but I am drawing the product straightforward, which would be the major, which would be the minor. Say for example, I have formed this according to the Markov addition. Say this is CH, this is CH3, and just to remind you what is the Markov rule, during the addition of the this HBr or such kind of the species like HCl, other things, to the unsaturated system, the negative part of the attacking reagent, that is Br negative, right, will join that carbon atom around the multiple bond which have the lesser number of the hydrogens. So this is the multiple bond, and around the multiple bond we are having CH and CH2. So according to the Marconi, this Br should go to this CH to form the major product actually. So here I have formed a major product, and the question it is saying that A major, right? Regioisomer A is the major. So we can straightforward say this is my type A compound. Okay, and then I can draw the minor one also. In the minor one, what you do, you put hydrogen here at CH and you put bromine at CH2 Br. So this is your minor product, and this I am calling as B. Okay, now what you can do, you can quickly assign the chemical shift for these species. So how we can assign the chemical shift for these species, it is quite interesting and quite important, right? You see, this hydrogen, this is only one hydrogen, and this one hydrogen in the environment of the bromine, bromine is very bromine is electronegative compared to this hydrogen or the carbon. So this electronegative bromine will cause the de-shielding, and de-shielding causes the downfield shift. Downfield shift means higher ppm value. That means this hydrogen will appear at the highest ppm value, and that highest ppm value is 5.17. Okay, so what I can do, I can write the chemical shift of this one 5.17 ppm. Okay, I can write the ppm. Now next high is the 3.53 chemical shift. You see, again this is the bromine, but these are the two hydrogens. So see, this bromine will cause the electron deficiency now for these two hydrogens, right? So the electron deficiency would be higher around this carbon, right, due to this bromine, but not that higher that we have saw for this CH, because only one hydrogen is here. Two hydrogen little higher in number. So second higher chemical shift for this one, right? So I can write the chemical shift of this also, and these two hydrogen, it is 5.53, right? It is quite easy, and you know, then this should be 3.51 ppm, 3.51 ppm. Why? Because you see here these hydrogen is having the bromine here. Okay, and these are the number, these hydrogens are in 2 in number, right? And these are the 3 hydrogens. So this bromine will have little effect on this one. So this will have the very upfield shift. So it will have the chemical shift of 2.0. So that's why actually I love this problem, because this problem involves the various concepts. So I can write 2.0. Okay, ppm. Got it? There is no problem in that. So what I can do, I can mark these hydrogens also. Say for example, I can call this hydrogen as type A, and second you see, I can call it as type B. These hydrogens I can call it as type C. This hydrogen I can call it as type D. So what I can do, I can arrange the chemical shift. You see, highest was 5.17, second was 3.53, third was 3.15, and this was 2.0. So this 2.0, guys, you see this 2.0 value is actually for type B proton. So I can write B here. Okay. Similarly, this 5.17 for type A. So 5.17 corresponding to the type A. So I can write A here. Similarly, I can write D for this one. I can write C for this one, right? You can check here 3.53 D kinds of the protons having this chemical shift. You see D kind of the protons are having these kinds of the chemical shift. So this is how you can mark them. Now if you check the intensity again are in the order of these chemical shift actually. So 2 is for A. So here what you can do, you can write the intensity 2. And next intensity is 1, this which is for D, another is 1 which is for D, and then 6 which is for B. So this is very important. This thing is very important, that the order of the chemical shift actually is corresponding to the 2, 1, 1, 6. That's why respectively is written here, because 5.17 is corresponding to 2 and 3.53 is corresponding to 1 and 3.15 is corresponding to 1 and 2.0 is corresponding to 1, right? This is like this is how actually we can, first of all we can do this much of exercise. Once you have done this kind of the exercise, then you can solve your problem, right? Say this was my compound A, which was CHBr and CH3, and my minor one, which is the isomer B, which is CH2Br, right? The condition was like that. And very quickly what I can do, I can mark all of them. Say this is A type of these are the A types of the protons, these are the B types of the proton, these are the C, and these are the D. Chemical shift, you know, this one is having the see, earlier I already solved, this is having the highest value, A is having the highest value, right? How we have how we have done all these things. Now if you go back here, you see we have what we have done, A, D, C, B. I have arranged in this manner. So whatever the answer will have now, we'll arrange the things in that manner. A, D, C, B. Now suppose my first option is 3:2. Suppose if I take this molar ratio of 3:2. So what is the meaning of this molar ratio of 3:2? Say I have taken 3 and 2 of this, 3:2. So type A type of the protons, see here you can see 1 hydrogen is there and 3. So 3 1 ja 3. So type A protons are 3. So I can write 3 here. And then you can go for here type B protons. Type B protons 3 number is here because the moles of 3 and 3 protons are there. So 3 3s are 9. So type B protons are 9. So I can write 9 here. Okay, I made a mistake, I'm sorry. I can write B here. Okay, this was the situation. Okay, and then you can go for this say type C. Type C actually belongs to the second isomer, which is the isomer minor one. So 2 2s are 4. So type C are 4 times. So you can write 4 here. And then you see type D, again you see 2 and their number is 2. So 2 2s are 4. So I can write 4 here. So the molar ratio for if I take the molar ratio of 3:2, right, where 3 corresponding to isomer A and 2 corresponding to the isomer B, then I'll get these intensity ratio 3:4:9, right? But in the question you can see, if I go back in the question itself, it is given 2 1 1 6. So I have to look for 2:1:1:6, and it should be A, it should be B, and then it should be D, it should be C, just like that, right? We have to check this one. Now suppose my second option is in the question 4:1. Suppose I take the molar ratio of the 4:1. So what I can do, I can write here molar ratio of 4:1, that means 4A and 1B. So what we'll get in that case? 4 type A protons are 1 only, type A proton is 1 only, right? So 4 1s are 4. So we can write 4 here. And then you can see type B protons, and again you see 4 moles I have taken for this A, So 4 3s are 12. So type B protons are 12 in number. So for type B I can write 12 here. Then you can go for type C. I have taken the molar ratio of 1. So 1 into 2, that is 2. So for type C I can write 2 here. Similarly, this is again I have taken the molar ratio of 1. In fact, if I check for D, so 2 are here. So 1 into 2, that is 2. So what I can do, I can write 2 here. So I am getting this molar ratio, 4:2:12. So if you want, then you can simplify it, right? And if you simplify it, then you will get your answer. Say suppose 2 2s are 4, 2 1s are 2, 2 1s are 2, 2 6 are 12. Okay. So simplified ratio is that. Simplified ratio is that. That means molar ratio of 4:1 is corresponding to the integration or the intensity which we are looking for. That means my option B is the correct answer. So this question is very tricky question and very important question, and personally I loved this question pretty much. Now moving to the next problem, what it says. Yes, this is the problem. See, this is the problem from the physical spectroscopy part, right? And in the first look, if you see the question for the first time, then you will see, oh, what is this actually? This is quite difficult, how to solve that. But see, you will take only 30 seconds. Believe me, if you know the concept of the physical spectroscopy, if you have learned the spectroscopy, the physical aspects of the spectroscopy or the physics of the spectroscopy in pretty much detail, and you have memorized the question, then you will take only 30 seconds to solve this kind of the question. First of all, how actually we will check this 30 seconds, how we can solve in the 30 seconds. You see, one magnetic field is 1.5 and another magnetic field is 1.5, right? Rest all things in the Boltzmann distribution law, right, or Boltzmann equation, all other things are the constant. The only varied things are these two, 7 and 1.5. Very quickly you can take the difference of 7.0 and 1.5, okay, and it will quickly give you 5.5. So this 5.5 is there only this option, and you can blindly mark this option A is the correct answer. And yes, option A is the correct answer in that case. So in the first instance you can get this answer, right? This how easy this question is. But if you want, then you can go for the physics also. So how we can go for the physics of this compound? Let me erase the things which I have shown you. See here, first of all, I am writing the population of the nuclei in the excited state. So how actually say in the excited state, what the question says, in the excited state is n dash and ground state is n. The population of proton spins in the highest energy level of the sample, the magnetic fields of this and this are n dash and okay. So when you have the magnetic field of 1.5, then the value is n dash, and when you have the magnetic value of the 7.0, then the value of nuclei, number of the nuclei should be n, right? Rest you know, the gyromagnetic ratio, Planck's constant, Boltzmann constant, temperature, all things are the constant, taken constant. And here one very important thing is there, the partition function is assumed to be 1. There is no need to go in that much of the detail. If you simply apply the Boltzmann distribution law, then you will get to the answer, right? So why to go for such complications? You simply know, in the excited state, say this is n dash, and you know the Boltzmann distribution law, this is e to the power of negative gamma, which is the gyromagnetic ratio. This is the H cross, but please remember, this is H cross, this is not H. There is a difference between H cross and H, right? H cross is equal to H upon 2 pi, right? You know, and this is H cross. And next thing is the your magnetic field, okay? In that case, your magnetic field, say suppose B0 dash, right, divided by KT. I can take this as constant. Say this is my equation number 1, okay? And then the population in the ground state, suppose in the ground state this is n only. So you can write e to the power of negative gamma H cross B naught divided by KT. There is no problem in that. Say suppose this is equation number 2. If you take the ratio, that is n dash by n. If you take the ratio of this, what you left with, e to the power of negative gamma H cross multiplied by B dash 0 by kt, and this should be divided by e to the power of negative gamma H cross B0 by kt. This is the ratio. If you solve this, then you will get e to the power of negative gamma H cross B0 dash divided by kt, right? And remember, you have actually moving this this your exponential function from denominator to the numerator. So this negative will become positive when you go up, right? So I am moving from this denominator to the numerator. This much of little mathematics you should know while solving such kind of the physical spectroscopy problems or the physical chemistry problems. So this would be now gamma H cross B0 by kt. Now you see guys, in that case what is happening here? Gamma H cross constant, kt constant. The only thing which is changing is what? Magnetic field. First is 1.5 and second is your 7.0. Only thing is only this thing is happening here. So if you solve this, right, don't forget the log values, right, or how to apply the log rules. So this will give you e to the power of gamma H divided by kt, gamma H cross by kt. So let me write it in the little good manner. This is kt. Okay, so what we have done, we have taken this value first here. So we'll take the B0 first here, right? So we'll take the B0 here, and you know this is negative sign, sorry, you know this is negative sign, so this B0, so negative B0 dash. So I can write negative B0 dash. Only this thing you need to do, and you know this will remain like that, gamma H cross divided by kt, and this is what? 7.0 minus 1.5, and this will give you what? E gamma H cross divided by kt, and this is your 5.5. So because it is in the power, right? Because this B you see here, please remember this B0 is in the power here, right? So this 5.5 is in the power here. So if you take the log on the both sides, so what I can do, I can say take log on both sides. Okay, so what will happen? You will get ln n dash by n, and since this was in the, this 5 actually is in the power of this one, so the log m to the power n, see this formula you should know, log m to the power n equals to n log m. That means the power will come here. So this 5.5 actually, which is in the power here, because B0 is in the power of this E, so this will come here. We will write 5.5 and rest thing gamma H cross divided by kt is the constant. So my answer is, again you can see this one, A. So this is how you can solve the problem. Okay, so these are the 5 problems, right, which is from your June 2019 examination. So if you are watching for video for the first time, please subscribe the Untitled Chemistry classes to share with your friends also. Okay, and if you have any difficulty in any kind of the explanation, then you can comment in the comment section. Okay guys, so that's it for today from the Untitled Chemistry classes. So we'll meet you again in the next class with the with the December 2019 examination. Thank you, thanks for watching.